Welcome back. Let's do current, voltage, power, and energy in an inductor. So we're given basically this waveform right here, where you have a current in milliamps changing over time in milliseconds. We need to be careful with the units in this thing. It's a little tricky. So goes up to 250 milliamps at 5 milliseconds, and then goes back down to 0 at 10 milliseconds. So that's given, and also this circuit's given here. So we've got a current source connected to an inductor. So there's going to be a voltage across this inductor with this reference current I. So I is changing over time, and what we're asked to find is the basically I of t, V of t, power as a function of time, and the energy as a function of time. What are all of these guys? And the way we're going to do that is we're given I of t, and we know V equals Li prime, and we know P equals IV, and we also know this W is 1/2 Li squared. We know that, but it turns out that W is also given by the integral, the area under the curve of the power, which turns out to be useful in this thing. Because remember, power is the rate of change of energies, or the inverse of that is if you integrate the area under the power curve, you get the energy. So yeah, so that's what we're going to do. So let's try and be organized about this. So we're going to do this mathematically. So we're going to do this with the equations. So let's look at this thing and come up with the equation for this thing. So the slope of this guy is the rise over the run, and it's rising 250 times 10 to the minus 3, 250 milliamps. It's rising over 5, over this interval right here, over 5 times 10 to the minus 3 seconds. These cancel, and you get 50, and the base units amps and seconds, because I entered, this is 250 times 10 to the minus 3 is amps, and 5 times 10 to the minus 3 is seconds. So the final unit of the slope is amps seconds. It's base units. So basically, for I of t, what we've got is we've got two different time intervals. We've got from 0 to 5, and then from 5 to 10. So the equation of the line I is 50t basically. This is going to be amps, and you have to kind of think about that, because the slope is base units amps, and when you put in the milliseconds in here, you're going to get milliamps out. So that's what the base units are amps, and this is from 0 to 5 milliseconds. Okay, then the equation of the line for this second interval right here, it's going to have a negative slope, and then the y-intercept, if you carried it up to here, would be 500. So the equation becomes the y-intercept 0.5 minus, and then the slope of minus 50. It becomes that. This is the equation of the line for the second interval between 5 and 10 milliseconds. And then you got to stop and think, is that going to work if you put in some numbers? So if you put in time in milliseconds, I would get milliamps out of this. And if I put in, and this is already in milliamps, 500 milliamps. So it looks good. So that's the current. Okay, the voltage as a function of time, we're just going to use this formula. This one, V equals Li prime. So, oh, I didn't give L. L is 20 millihenries. That's the inductance of this guy right here. So we're just going to use that times I prime. So for the first interval from 0 to 5, we're going to take the derivative of this guy. So V is Li prime. It's L, which is 20 times 10 to the minus 3 henries. So 20 millihenries. I'm just putting in base henries because there's all these. You got to be careful with the units. So that's base henries, and the derivative of 50t is just 50. So you work this out, and it turns out to be 1. And we're dealing with amps and henries. So we have base volts, not millivolts or anything like that, but just volts. I'm going to put a box around that so I don't lose it. So this is the first time interval. Okay, the second time interval here, same thing, but we'll just use the second. We'll take the derivative of this guy. Well, first it's henries. L is henries times 10 to the minus 3. 20 times 10 to the minus 3 henries. Then the derivative of this, so the derivative of this constant is just 0, and the derivative of minus, well, the derivative of 50t is 50, and then there's a minus sign, or you could think of it as the derivative of minus 50t. Anyway, there's a minus sign in there. Minus 50, it turns out to be minus 1 volt. So this is between 5 and 10 milliseconds. Okay, that's the voltage. And the power, once again, we do it over 2 intervals. So the first interval from 0 to 5, we're just going to multiply these 2 equations together. Here, I could put a box around this guy, I guess. So 50t times 1, so 50t amps times 1 volt is 50t watts from 0 to 5 milliseconds. Second interval, it's just this equation is just the whole equation I times whole equation V's. So 0.5 minus 50t times minus 1, which works out to just multiplying a minus 1 in this thing. It ends up with 50t minus 0.5 watts. So this is from 5 to 10 milliseconds. That's that guy. Okay, lastly, the energy is a function of time. So like we have 2 ways to do that, and the first way will work for the first interval, and then we have the second way, which we need to use for the second interval. You could use this second way for both intervals here, the 0 to 5 and the 5 to t, and it would work. But let's just, to show you that there's 2 different ways to do it, let's for the first interval, I'm just going to use W equals 1/2 Li squared. So plug in, I'm sorry, 20 times 10 to the minus 3, that's L, and I is just 50t over that interval. So it's 50t quantity squared. Just plugging in the equation for I into this formula, and what you end up with here, if you work it all out, surprisingly, is 25t squared. And this is in joules, and this is from 0 to 5 milliseconds. That's that guy. Now that it's harder to get that to work for the second guy because you've got the time in interval, although you could, if you're very careful, you could get this formula to work. But just to show you that there's another way to do it, let's use this area under the curve thing. And then I'll show you graphically how this looks too. But anyways, so the second interval, let's just use the fact that the energy is given by the area under the curve. And I'm using x as my substitution variable because I need to take an interval from t0 to t, all right, to get a function of time. So this is going to be the interval from, and I'll use base units, 0.005 milliseconds to t. So I'm trying to integrate this equation from 5 to t, and this is the kind of a calculus review, what you do in calculus. the equation of, or P of t during that time, in that time interval is this dude right here. So it's going to be 50t minus 0.5 dx. So that's P of t, but I'm using P of x because I'm integrating. So I'm substituting. Oh, this should be an x. 50x minus 0.5 dx integrated from 0.005 to t. And so the tricky part, well, that was a little bit tricky just by itself, but the trickier part is that we can't just start nowhere. We can't just start out in space. I mean, there was initial energy that was, you know, that was present. So we have to add that in there. So you have to add the energy, the initial energy at 0.005. Okay. Just kind of a calculus thing. Now I think we'll look at this on the graph and talk about it more there. But go ahead and integrate in this thing. So the integral of this junk in here is going to be 25x squared minus 0.5x. So, right, you get 1/2 x squared, should be 25x squared, and then you end up with 0.5x, that guy there. And those whole things are, this whole thing is evaluated from 0.005 to t, plus this initial energy here. We can use our previous solution. So it's going to be 25 t squared, where t is 0.005. So this is the energy at 5 milliseconds. Right, this guy gives us the energy after that, but we have to include the energy from the starting point. Just a kind of a weird thing that you got to do, right? So now you have to plug in the limits of integration, right? This thing here. So it's the value at the top minus the value at the bottom. So this guy ends up being 25 t squared. That's why we used x, because now we're plugging in t. So 25t squared minus 0.5 t, that's the value at the top, minus the value at the bottom, which is 0.005 squared, plus 0.5 and then bringing this guy down, plus 25 0.005 squared, and I multiply the negative sign through these two terms here. The negative sign from the plugging in the limits of integration. These two coincidentally happen to be the same, so they cancel, and you end up with 25t squared minus 0.5t plus this quantity, which is 2.5 times 10 to the minus 3 joules, and that's from 5 to 10 milliseconds. Okay, a bit of a mess, but what does this look like if we graph all of this stuff? So just to compare these guys straight down vertically, I'm going to redraw this current graph. So the current graph goes up like that, and then it comes down, and it's at 250 and 10, and this is 5. And this is I in milliamps and T in milliseconds. That was given. And then graphing this guy, voltage, it goes from 1 to so we could bring this 5 all the way down in all of these curves. It goes from 1 and then it flips to -1. So it's 1 for a little bit and then it flips to -1, right? It's 1 from in the first time interval, and then it flips to -1 in the second time interval. And then the power does this. So this is V in volts, and this is the power in watts, and the time in milliseconds. It does that. This curve here is just 50T, so it comes up to 50 watts at 5 milliseconds. And no, not 50. It comes up to 0.25 watts, or 250 milliwatts. And then it does this thing. So it's coming into the device and then immediately flips instantaneously to leaving the device, and then decreasing in the rate, decreasing. And then the W curve is going to be positive the whole way, because this is the energy stored in the device, so it's always going to be positive. And it comes up like this squared thingy, this 25T squared. So it's just like that kind of thing. So this is the energy in joules, and it comes up to, if you solve this initial value, which I didn't, but if you solved it for it, it'd be 600 or 625 millijoules. And this ugly noise right here really is just the flip side of that guy. So I was saying you could, conceivably get it using this formula, but it's really easy. I don't know, it's easy to get mixed up, but that's what this is. It's just the flip side of that. It's a mirror on either side. So we can sort of talk about this graphically, what's going on here. So I've got I coming up at a constant rate, so the derivative is constant, so I have a constant velocity, and then here, or constant voltage, and then here the slope changes direction and stays at a constant slope, so it becomes negative, and so this becomes negative. And then if you multiply a positive times a positive, you get a positive for the power, and a positive times a negative, you get a negative for the power. So power is entering the device at a constant rate and then immediately flips to leaving the device at a constant rate. The area under this curve is the energy, and this is just a triangle, by the way. So the area of this guy is the area of a triangle. It's 1/2 the height times the width. This ends up to the 0.625, which is what we see down here. Okay, so the area under the curve is this thing, and so you could integrate this and get this equation for the instantaneous value. Okay, which at this point, right, this is instantaneous energy change. So you could at any point on here, it gives you the energy at that instant, but at this instant, it's equal to this area. Kind of related to calculus, all of this stuff, right? Then the energy starts leaving. So here it's climbing and coming into the device, and we reach a maximum amount of energy as the power flows into the device. Then the power starts flowing out of the device, so the total energy stored starts to come down. Okay, so trying to relate calculus, a lot of review of excuse me, a lot of review of how to do some of these calculus things if it's been a while for you, and what those graphs look like, and then try and relate those graphs to what's physically happening. Okay, that's it. Hope that was useful for you. See you next time. Thanks.